In this series of lectures, we plan to cover Module 3 of our course, Heat and Mass Transfer. It is a sort of a miscellaneous module comprising of roughly the three parts listed. Part 1, Transient Heat Conduction, wherein we deal with methods to analyze unsteady, otherwise called as transient heat conduction. Part 2, Analysis of fins. This deals with preliminary analysis of extended surfaces called fins that are used to enhance the rate of convective heat transfer. Part 3, Boiling and condensation. This mode of heat transfer demands a separate analysis because unlike any other heat transfer methods that we have learned, heat transfer by boiling and condensation involves phase change at a constant temperature. Quantitatively, this mode of heat transfer can have very high values of heat transfer rates. So let's first take up transient heat conduction. From what we have learned in the first module, the general three-dimensional heat conduction equation is as given here. If you solve this differential equation, the solution expected is temperature as a function of x, y, z and time t. If you make an assumption of steady state heat conduction as we did in the first module, you will have temperature as a function of just the spatial coordinates x, y and z. But if the situation remains unsteady or transient in nature, temperature is a function of x, y, z and also the time t. Let's now describe an example to illustrate the case of unsteady or transient heat conduction. Consider a piece of red hot iron, say at a temperature of Ti, dropped into oil at temperature T infinity as a part of some heat treatment process. Imagine that you are an engineer studying the austenite to martensite transformation and you wish to calculate at what rate is the hot piece of iron being cooled, what is the temperature of iron, say after a time interval delta T. To answer such questions, you need to appreciate that the temperature T of this piece of iron is varying in a fashion as described in this figure. Examples like these, wherein the temperature is a function of time, are called unsteady or transient heat transfer problems. The easiest of all transient heat conduction methods, and the only one that we have to learn, is the lumped system analysis. This method assumes the body to have a uniform temperature distribution. Continuing from our example for transient heat conduction, let a hot piece of iron be immersed in a fluid at temperature T infinity. If I assume this hot piece of iron to be at uniform temperature at all instances of time, I mean to say that at any one point of time, if I take the temperature distribution, it shall be same throughout. The temperature at this point shall be T, at any other point shall be T, let it be on the inside of the body or be it on the outer surface of the body. At all points, the temperature shall be the same value, say T. This assumption of uniform temperature simplifies the complicated temperature distribution, temperature as a function of x, y, z and time T, to a very simple temperature as a function of time. This is because temperature with uniform distribution becomes independent of the spatial coordinates x, y, z. Any point you take in this domain, you have the same temperature. So temperature becomes independent of the spatial coordinates and only dependent on the value of time t. Let us now get into the details of the method. Consider a body of mass m, volume v, surface area as, density rho, specific heat C, and with an initial temperature Ti. Let this body at time t equal to 0 be placed in a convective medium of initial temperature T infinity, and the heat transfer coefficient between this body and this convective medium be h. Similar to the example that we considered, let us take the case of a hot body immersed in a colder surrounding fluid. So that is, the initial temperature of the body Ti is greater than the surrounding fluid temperature T infinity. In such a situation, we would know that the hot body would be losing heat continuously to the colder fluid until T, the temperature of the body, is same as T infinity. So at any instant of time, the hot body would be losing heat to the surrounding fluid through convection. For a very small incremental time dt, the decrease in internal energy of the body shall be equal to the convective heat loss from the body. Using the nomenclature that we described before, convective heat loss from the body may be expressed as HA delta T. H is the heat transfer coefficient between the body and the fluid. A is the surface area of the body. T is the temperature of the body at this particular instant of time. T infinity is the temperature of the surrounding fluid. The decrease in the internal energy of the body is minus mc dt, where m is the mass, c is the specific heat, dt is a change in temperature during this incremental time dt. The mass of the body may be expressed as density times volume. Taking temperature terms to this side and the rest to the other side, you finally get to this form. We have taken T infinity to be constant. Therefore, differential of T minus T infinity is going to be dt minus dt infinity, and T infinity being a constant, dt infinity equal to 0. Therefore, we have d of T minus T infinity equals dt. Now, substituting this in the above equation, we have HAS divided by rho CV dt equals d of T minus T infinity divided by T infinity. Now, integrating from t equal to 0 to some general time t, and using the initial condition that at time equal to 0 the temperature of the hot body was Ti, we do this integration. Applying the respective limits and realizing that this part of the equation is of the form integral dx by x, we integrate to get this form of the equation. Rearranging in exponential terms, the equation takes this form, and we realize that this is the equation that we wanted. The equation that connects the temperature at any instant with the particular time. Let's discuss some important points with respect to the lumped system analysis. We had arrived at the final relation in this form. If we take HAS divided by rho CV as B and plot the temperature versus time graph for different values of constant B, you will see that for higher values of B, we see steeper fall in temperature with respect to time. Point 2. By simple inspection, it may be observed that the dimensions of rho CV divided by HAS is going to be that corresponding to time, so namely seconds. And in fact, this term is called the time constant for the system. Now, the third and the most important point with respect to the lumped system analysis, it is applicable in cases when Biot's number is less than 1, where Biot's number is defined as HL divided by K. L is the characteristic length, which is arrived at using this equation, volume divided by the surface area. It may be rearranged to explain its physical significance. HL by K may be adjusted as L divided by Ka divided by 1 by Ha, where L by Ka is the conduction resistance and 1 by Ha is the convection resistance. I just said for the lumped system analysis to be applicable, Biot's number has to be less than 0.1. It means that the conduction resistance must be significantly less than the convective resistance experienced by the system. So if the conduction resistance within the system is very small, it means that throughout the body, the temperature is going to be uniform. With the basics of the lumped system analysis explained, let us solve a typical problem. In quench hardening process, steel rods, the density, the specific heat and conductivity are given. Steel rods are heated in a furnace to a temperature of 850 degrees Celsius and then cooled in a water bath to 95 degrees Celsius. Water bath is maintained at 40 degrees Celsius. The convective heat transfer coefficient is given as 450 watts per meter square Kelvin. If the steel rods have a diameter of 50 mm and a length of 2 meters, determine 1. The time required to cool a steel rod from 850 to 95 degrees Celsius in a water bath. The total heat transfer to water during the quenching of a rod. The first step in any lumped system analysis is to check for the criterion of Biot's number less than 0.1. First, calculate the characteristic length. LC is the volume divided by the surface area. So for a steel rod of length L and diameter D, volume is pi d square divided by 4 times L. The surface area AS is pi dl. So that ratio turns out to be d by 4 and has a value of 0.0125 meters. Now Biot's number is HL by K. Now substituting these values, you get 0.088, which is obviously less than 0.1. So therefore Biot's number is less than 0.1, so you can apply the lumped system analysis. Using the equation from the lumped system analysis, you have this equation where B is calculated as HAS divided by rho CV. Now that has been calculated for you as 0.01059 second to the power minus 1. You're asked to find out what is the time taken by the steel rod to be cooled from 850 to 95 degrees Celsius in the water bath. To do that, so the temperature at the end is T, so that is 95 degrees Celsius. T infinity is the temperature of the water bath, that is given as 40 degrees Celsius. T initial, the initial temperature when it is taken from the furnace is 850 degrees Celsius. So again, substituting these values and taking log to find what is the value of T, you solve for T and get it to be equal to 254 seconds. The second part of the question asks you to find out what is the quantity of heat that needs to be removed from one steel rod. So that is estimated as mc delta T. M is expressed as density times volume, and hence substituting the values from the given quantities, you can find that the quantity of heat that needs to be removed is 10 megajoules. I will leave you with these questions. In the problem that we solved, if I asked you to estimate what is the rate of cooling, how would you find this rate of cooling? And what about its nature? Does that remain constant with respect to time? Does that decrease? Does that increase with respect to time? Now, my second query would be, heat is being added to the fluid surrounding the steel rod. With such a case, how can T infinity be a constant? And my third question, Biot's number is defined as HL divided by K. You have a very similar number in convection, that is Nusselt's number, which is also defined as HL by K. And what is the difference? So take some time and try to answer these questions.